Hello and welcome to Space. This month we're in Hanover to see how some incredibly precise machines are being made in order to better observe some of the most violent events in the cosmos. Things like black holes colliding and galaxies merging. But first, let's have a look at some other news from the universe this month. The first ever photos of dwarf planet Pluto from NASA's New Horizons spacecraft have shown it to be larger than previously thought, with a more varied range of features on its surface than expected. A new weather satellite has been launched offering nowcasting of heavy thunderstorms, cyclones and volcanic ash clouds. The MSG-4 satellite, operated by EUMETSAT, took off on an Ariane 5 from French Guiana. And Italy's Luca Parmitano is leading the latest NASA underwater training session in Florida. The ESA astronaut will spend 2 weeks beneath the ocean to test tools and techniques for spacewalks. To our main story now, and the quest to capture a signal from gravitational waves. 100 years ago, Albert Einstein predicted that our universe should be filled with something called gravitational waves. They're ripples in the fabric of space and time, and they could tell us a lot about mysterious objects like black holes. But we still don't know if Einstein was right, because we're still looking for them. It's proving to be quite a challenge.
Gravitational waves are coming from all over the universe. However, the fact that it's gravity, it passes through stars, galaxies, you, me, the Earth, everything.
A gravitational wave that would, for instance, come flying towards me would make me thinner and longer and squatter and fatter periodically, but only by very tiny degrees.
These elusive gravitational waves are extremely faint, so the devices designed to capture them are large and highly sensitive. This is one of Europe's biggest detectors, located near Hanover.
This here is GEO 600. It has 600-meter-long arms that extend this way and then at a right angle that way. And down here in this little trench, we have a vacuum tube that houses high-power laser beams inside. If you look down, then you can actually see the vacuum tube.
The experiment measures the relative difference in length between the two laser beams. A gravitational wave would make the two beams go out of phase by a tiny but measurable amount.
So far, we haven't found anything, but any minute now, a star could explode, and then we would see a signal.
With millions of potential sources all over the universe, expectations are high that if we can observe gravitational waves, it will be a revolution in astronomy.
It is a completely different, basically, window into the universe. What we're doing right now is observing the universe in electromagnetic waves and neutrinos, mostly. Gravitational waves will be a completely different way of looking at the universe, seeing things that do not emit what we would consider light.
The only type of radiation that a black hole emits directly is gravitational radiation, because a black hole can shake space and time around it, and those ripples in space-time, they propagate away from the black hole and tell us exactly the story about what it looks like and sounds like.
To improve our chances of observing gravitational waves, we're going to space. We'll be sending this pioneering ESA spacecraft that's unlike anything ever flown before.
Hey, good morning. So welcome. This is the LISA Pathfinder spacecraft. This is the spacecraft module of LISA Pathfinder, and this is going to get launched hopefully in around October this year.
LISA Pathfinder is, as the name suggests, showing the way forward and generating huge excitement.
I started working on spaceborne gravitational wave detectors. That days it was called the LISA mission, 21 years ago. So to stand here today, having this behind me is unbelievable. You know, it's taken 21 years to get here. There's been a lot of blood and tears en route, but now it's jubilation.
LISA Pathfinder won't actually measure gravitational waves. Instead, it will prove the technology, which centers around 2 free-floating gold-platinum cubes inside the spacecraft. If it works, then it will lead to a much bigger mission involving 3 spacecraft flying in formation.
The future, after we do LISA Pathfinder, we then take effectively 2 or 3 LISA Pathfinder spacecraft, we separate them by 5 million kilometers, we have 1 cube in each spacecraft, and we measure the distance between the cubes.
A fully functioning space observatory capturing signals from gravitational waves promises to be an awesome new tool.
Gravity is the fundamental force of the universe. At the largest scales of talking about stars, galaxies, the universe, they're dominated by gravity.
What we're doing hasn't been done before. We're doing things that haven't been seen before. We're looking for something that has been postulated 100 years ago, but has not been proven. I mean, how can we let that stand in the room, right?
All the universe interacts via gravity, and that gives us the hope that gravitational waves will really let us listen to the dark side of the universe. And who knows what's out there.
From black holes all the way back to the first moments after the Big Bang, gravitational wave astronomy could change how we see and hear the universe forever. Now we're heading to the Astronaut Academy in Cologne to hear some of the challenges of learning to spacewalk.
0.06 range rate. Target is nominal.
Here we train the ESA astronauts on the challenges required for spacewalk. Inside this big water tank, we immerse these modules, and with the tools over there, we start the training. One of the challenges during a spacewalk is that you have to be double tethered to the structure and to the station for safety reasons.
Luca, did you check that it is locked?
If you are lost in space, like in the Gravity movie, you can pull it and then you are back to the station. These boots have the same sole as the one of the spacesuit. And this is currently using this platform that an astronaut can lock himself with the feet and then be able to work with both hands. To simulate the helmet, we use this mask. And as you can see, we have a limited visibility inside. Jeremy, I'm your father. So it's very important to be trained to be safe and efficient.
Is there any damage notable? No, there is no damage. Everything is great. 0.
That's it for now. Next month, we'll have the latest news from our comet hunting friends Rosetta and Philae. See you then.